Okay, so this is our geometric centroid. And the geometric centroid is halfway. Okay? This distance from here to here is 1.5. Now, why do I say that? This is purely based on observation. Okay, so if I were to section this over here and section this on top, right? The thickness is 0.2 inch. The thickness is 0.2 inch, right? The sum of the cross-sectional area, the length or the width is 2 inches. This is also 2 inches, right? So whatever is at the top and at the bottom, based on cross-section or based on first moment of area or second moment of area, is the same. So when that's the case, right, you only have this vertical web, major web, to decide where the center is. So it's exactly at the center. So that is why I know that the geometric centroid is 1.5 inch from the top or 1.5 inch from the bottom. Okay, so that is why I say that we know where the geometric centroid is based on observation. Right. So we are going to find, I'm going to call that point C. Point C is exactly on our centroid. Okay. So what we know that at point A, at point B, and likewise at point C, right? The V over I ratio is a what? Constant. Right? We know that, right? So the V over I is constant at either point A, point B, or point C. So when we calculate shear stress at point A is equal to V over I Q at point A over T. And then when we calculate B, and then when we find C, right? So what we have to determine now, we have to determine the location where tau max will occur. Okay, so this is the first thing that we have to do. So now to determine where the maximum tau max will occur, we have to find the Q over T ratio. Remember I was last Tuesday, right? On Tuesday, we talked about this Q over T ratio. So now we have to find the location of the maximum shearing stress based on the Q. So once we have located the position of highest Q over T ratio, then we can find tau max, then we can use tau max is equal to V over I Q over T, and then we can determine the what? We can finally determine the V over I ratio, which is equal to tau max T over Q. Okay, so that is why for this problem, they did not give us no need for both absolute values of V and I. All we are interested is the ratio. To determine the V over I ratio, we have to know the position of the highest Q over T ratio. This is because tau max is given. Okay, so when you see a problem like this, don't rush and calculate the second moment of area. Okay, it is sometimes, for this case, sometimes not necessary. Okay, so this is how we are going to proceed to solve. Right. So before we go on, now I'm going to take that same figure. Okay, so the first thing we're going to do, we are going to design our shear flow Q. Okay, so from here, this is our Vy, and then this is our geometric centroid. Right, and then we design our Vy, our Q. Okay, so this is how our Q will look like. Right, so this is why I designed that way, because these are our major web. Okay, and this is our geometric centroid. Same, so when this is the case, this will be flowing in down here. So over here, this is our terminal 1. And then down here, over here, these are our terminal 2. And over here, this is our terminal 3. Okay. Right. So now, once we have finished this, we have to analyze our structure. Is this a box beam, or is it a white flange? So let me get the images. Okay, the figures for box beam. I don't like when they call that a neutral axis. Okay, it's a geometric centroid. You guys know that by now. So this is a box beam, and over here, this is a white flange. Okay. So what I'm going to do is I'm going to again take this. Okay. And now is naturally difficult to visualize, but I'm going to do something so you know whether is it a box beam or a white flange. So I'm going to, okay, and then I'm going to highlight the whole thing again. Maybe it won't work. Yeah, it did. Okay, so I'm going to call this above the centroid is our top, and below the centroid is our bottom. And then I'm going to cover, okay, I'm going to cover either the top or the bottom. Why I cover it? Because the first moment of area cannot cross the what? Cannot cross the centroid. Yes or no, right? That's the thing, that's the rules that we won't break. Okay. So when we look at the top, right? When we look at the top, when we design our shear flow, it looks like this. And over here, this is our terminal 1. And if I were to also have this cover the bottom, right? You can see that it's the same. We can have the concept of covering the bottom part because the first moment of area cannot cross the geometric centroid. So the top, what we have is the shear flow on the left, and then the other one flow towards the right, right? One Q go towards the left, one Q go towards the right. So for this case, on our problem, if we cover the bottom, we realize that this is a box beam. And when it's a box beam, we call it 2Q. Why 2Q? Because one Q go towards the left, the other Q go towards the right. Okay. Now, if we look at the other side now, okay, we look at the other side now. I'm going to cover, now I'm going to cover the white flange. I'm going to cover the top. Okay. So now I'm going to sketch the I'm going to sketch the shear flow of our structure. Okay, so we know the major web controls the okay. And this one we have terminal 1 over here. I call it terminal 1, okay. And then we have our terminal 2. Right? So if you look at the white flange, right, this is our terminal 1 and this is our terminal 2. So for white flange, below the structure, you have 2 terminals. Likewise, you have 2 terminals. And you have Q1 going one side and Q2 going to the other side. So you have Q1 going this side and the other side is our Q2. So T1 and T2 are what? Not connected. Oops, sorry. Are not T1 and T2 are not linked or are not related in terms of Q1 and Q2. Okay, so when that's the case, at the plot at the bottom, right, this is our white flange, and for your white flange, we just need to call Q, okay, because there's a single Q on one side, single Q on the other side. Whereas for a box beam, right, you have Q flowing to the left, Q flowing to the right, and it's linked by a terminal. Okay, what I propose is now we go for a 5 minutes break, and we come back again in 5 minutes time.